Let's talk about the difference between the mass number that an isotope has and the atomic mass that's listed on the periodic table. So before we use this example of magnesium, one isotope has a mass of 24 and the other isotope has a mass of 25. If you look at magnesium on the periodic table, the atomic number that it has right on top or in the corner is 12. There are 12 protons for magnesium, but the mass it lists is 24.31. So it's neither 24 nor 25. And if you look at the periodic table, you'll see that very few of the masses are close to whole numbers. They're in between numbers like this. And that's because that is an average mass. Of all the samples of magnesium that scientists have taken, the average mass of magnesium in those samples is 24.31 AMU, atomic mass units. So we can calculate atomic mass using these different isotopes, but it's not realistic to add up every single atom of magnesium 24 and every single atom of magnesium 25 and then count how many we've added and then divide by that number. That's the normal way we would get an average, but there's another way to get an average as well. And that is to take the mass of the isotope and multiply it by the fractional abundance. So what do we mean by fractional abundance? We're going to see this in an example here. I could tell you every student's score on an assignment. If we wanted to know the average score on an assignment, I could tell you every student's score, and you could add up all those scores and then divide it by the number of students. But what if I didn't want to list every single score, and I could just tell you, well, 50% of the students got 26 points and 50% of the students got 30 points. Then you don't have to know how many students there were or each individual student's score. If you know that half got 26 and half got 30, you could probably just think in your head that, well, it's probably halfway in between 26 and 30. The average is probably 28. But you can also use this formula. So what is this formula saying? What is the fractional abundance? If you have something that's 50%, then that is the way it is written as a percent. If you write it as a fraction, remember that percent sign means per 100 or over 100. So our fraction would be 50 over 100, or 1/2 if we simplified it. Actually, if you write it this way, it's 50 hundredths. That's how you would write that, because this is 50 over 100 is 0.5. So we are going to use this. So we are using this as our fractional abundance. So we are going to multiply the fractional abundance times, in this case, the score. So we have 50% of the students getting 26 points, and we have 50% of the students getting 30 points. And then we're going to take the sum of that, we're going to add it up. So that's why I'm doing it up and down like this. 50% of 26 is 13 points. 0.5 times 30 is 15 points. So we get our average score of 28 points, which we, pretty much predicted that since half and half got 26 and 30, the average is going to be halfway in between. So here we have it, 28. Some students get confused and think, well, you just averaged 26 and 30, and that's not really true. So I wanted to pick something where it wasn't half and half. So you can probably tell that if 75% of students got 26 and only 25% got 30, then that's going to lower the average. We have more students with the lower score, so the average should be lower than 28 in this case. If we multiply 0.75 times 26 points, now this gives us 19.5 points. And then 0.25 times 30 points is 7.5 points. And then when we add up these results, we get a score of 27 points. So this is the method we can use when we calculate the average atomic mass. Since we don't know each individual atom's mass, and it's nearly impossible to count how many atoms we have, we can just use the percentages and the masses like this. So the next page has a few examples. We'll just go through all those examples. Instead of the percents, remember we're going to use the fractions. 91.75% is 0.9175. And we're going to multiply that by the mass of that particular isotope. Then we have iron 54 isotope, where 5.85% or 0.0585 is the abundance, and we're multiplying that by the mass. And then we have the least abundant isotope, iron 58, which has a mass of 57.933. It's only 0.28%, which is 0.0028 when we write it as a fraction. Okay, so I've written out what my calculator gives me. Not surprisingly, there are a lot of digits. Let's go ahead and take a look at the significant digits of these operations. We have a percent, or we have a fraction now that has 4 significant digits. These masses all have 6 significant digits, but then the answer would have 4 significant digits. I'm going to underline the place value because I'll be adding these up and figuring out the place value of where I can report this average atomic mass. This one, the fraction only has 3 significant digits, so the answer would only have 3. Same with this one, 3 significant digits, and for this one it would have 2 significant digits. So coincidentally, all of these are known to past the decimal, so when we add these up, we can keep it 2 past the decimal. So here we have the sum of all of these masses, and then we can report this to 2 past the decimal, so 55.84 AMU. And if we look at the different masses that we are adding up, most of the iron is close to 55.9, and then there's a few other masses, so coming out with an answer that's 55.8 is not very surprising. So it's always good to take a look and just make sure that your answer makes sense. Some students misplace a decimal point or do some sort of error when they're working with all these digits, but a lot of times your errors will give you an answer that doesn't make sense at all. So just double check and see if it makes sense so that you can catch any errors that you might be doing. Okay, let's try one more example here. A lot of times I will give examples like this where I have made up numbers that are not in agreement with what we have on our periodic table, because I want people to be able to do the calculation, not just look at the periodic table to see what kind of answer they expect. All right, so I've done these multiplications. This time our fractional abundances coming from our percents have 5 significant digits. So for all these measurements, we can go 3 past the decimal. And the sum can go 3 past the decimal as well. So we can report 84.063 AMU, which makes sense because about half of the krypton is close to 86 AMU, and then the other half is a little bit lower, so it ends up being lower than 86. This last question is more of a big picture question. I didn't want people to get too bogged down in all the calculations and not really have a feeling for what this means. So if we have 2 different isotopes, lithium-6 and lithium-7, making up the lithium that we have here on Earth, and we see that in the periodic table we report, or we can find that the average atomic mass is 6.94. So if you have 2 possible scores on homeworks, 6s and 7s, and your average on homework is 6.94, then that would mean that mostly you've been getting 7s because your average is closer to 7 than it is to 6. So we can deduce that most of Earth's lithium is lithium-7 because the average mass is very close to 7. I wanted to encourage you to play around with the simulator that I linked in Module 3 on this Fun with Isotopes page. So the second one shows how the atomic mass is related to the isotopic abundance. If we look at this mixtures, Then we can make a mix of isotopes. Let's go ahead and play with lithium some more. So if you pick lithium, we have lithium-6 over here and lithium-7 over here. If all the lithium on Earth were lithium-6, this would be the mass. This is the mass of the lithium-6 isotope. It's close to 6, it's not exactly 6. If it were all lithium-7, we would have this mass. If it were half and half, so half lithium-6 and half lithium-7, it would be sort of in the middle, very close to 6.5. If we want to see what it really is, you can click Nature's Mix, and it will show you lots and lots of green, so mostly lithium-7, about 92.4% lithium-7, and only 7.59% of the lithium-6. The little purple ones occasionally is what you'll find. So that is something you can play around with. You can either do buckets or you can do the slider. You can just make a percent. If you want to make it 50%, you can. 50% and 50%. So here again, we get about 6.5. And another link that I put on this Fun with Isotopes page down at the bottom, so maybe it's easy to miss, is this interactive isotope periodic table. This one is interesting because it gives the abundances that we actually do have on this planet for several of the elements. So we could take a look at lithium. You can see what the atomic mass and the percentage is for each of the isotopes. Isotope 6 and isotope 7. We have these over here. There are some elements that have quite a number of different isotopes that you can take a look at and see the percentage and the atomic mass if you just click on here on these dots. There are a few elements, the elements with a blue background, that only have one known isotope. So you can click around here and see what is known about the isotopes of the elements here.